Good morning. Welcome you all to the second part of the chapter Relations and Functions. In the last class, we discussed three types of relations. First one is reflexive relation. Do you remember what is a reflexive relation? Yes. A reflexive relation is a relation on a set A satisfying the condition AA belongs to R for every A belongs to capital A. Second type is symmetric relation. What is a symmetric relation? For every AB belongs to R, BA also belongs to R. That is called symmetric relation. Third type of relation is transitive relation. For a relation to be transitive, the condition is that if AB and BC are in R, then AC must belongs to R. Hope all of you learn these concepts well. Today, we are going to learn the fourth type of relation. For that, listen carefully. Here there is a set capital A containing four elements 1, 2, 3, 4. I am going to define a relation on this set A. Clearly, R is a subset of A cross A. Hence, it is a relation on A. Observe this relation carefully. The elements of capital R are 1, 1, 2, 2, 3, 3, 4, 4, 1, 2 and 2, 1. What are the peculiarities do you observing on this relation R? Is this relation reflexive? Of course. Why we say that this relation is reflexive? Here 1 belongs to A, 1 1 belongs to R, 2 belongs to A, 2 2 belongs to R, 3 belongs to A, 3 3 belongs to R, 4 belongs to A, 4 4 belongs to R. For every A in capital A belongs to R. Therefore, this relation is reflexive. What about the symmetry? Is this relation symmetric? To check it, we have to check each ordered pair. Suppose this is AB. AB belongs to R. Then what is BA? It is again 1 1. BA belongs to R. 2 2. The reverse element 2 2 is again in R. 3 3 4 4 are clear. Its reverse elements belongs to R. What about 1 2? When we reverse this ordered pair 1 2, we get 2 1. Yeah, this here 2 1 is here. Okay. When we reverse the element 2 1, we get 1 2, that is here. It means that for every AB in this relation, BA also belongs to the same relation. Therefore, the relation is symmetric. Now, let us check the last one, transitivity. For that, take the first ordered pair 1 1. What is the second component? 1. Now we are searching for another ordered pair starting with 1. AB belongs to R, BC. AB, BC belongs to R. Then AC belongs to R. That is the condition for transitivity. Okay. 1, 1. Second component is 1. We are searching for another ordered pair starting with 1. Okay. Yes. Here is it. Okay. 1, 2. 1, 1 belongs to R. 1, 2 belongs to R. Then 1, 2 is AC. That is also belongs to R. Okay. Then next one 2, 2 belongs to R. Then another ordered pair starting with 2 is this 2, 1. 2, 2 belongs to R. 2, 1 belongs to R. Then AC is 2, 1. That is again belongs to R. Okay. Then next 3, 3. There is no ordered pair starting with 3. 4, 4. There is no ordered pair starting with the second component 4. Then 1, 2. 2, 1. Starting with 2, then 1 1 must be in this relation for transitive. Clearly 1 1 is here. and 2 1 1 2 is here, 2 1 1 2, then 2 2 must be here. It is also clear. It means that for every two pairs AB and BC in R, AC also in R. Therefore, the relation is transitive. Okay. Then this relation R is a reflexive, symmetric and transitive relation on the set A. Such relations are called equivalence relations. Such relations are called equivalence relation. When we say that a relation is an equivalence relation, that relation must be reflexive, symmetric and transitive. Here the relation R is an equivalence relation on A. Can you give another example for an equivalence relation on the set A? Of course. What is that? A cross A. We know that A cross A is a reflexive, symmetric and transitive relation for any set capital A. Can you find another one, a simple one, equivalence relation on this set? Yes. What is that? Identity relation. What is an identity relation on this set? R equal to 1 1 2 2 3 3 4 4, containing 4 elements. That relation is equivalence. Why? It is reflexive, symmetric and transitive. Or in short, a relation is said to be equivalence if it is reflexive, symmetric and transitive. Let us write its formal definition. Okay, a relation capital R on a set capital A is said to be equivalence if it is reflexive, symmetric and transitive. Say with me, a relation is equivalence if it is reflexive, symmetric and transitive. Now we have learned what is an equivalence relation, that is the fourth type of relation. Okay, now let us look at the important notes of the equivalence relation. First one, as we discussed before, let us discuss about A cross A. What about A cross A? Is A cross A in equivalence relation? Yes, A cross A is equivalence. Okay, A cross A is equivalence because A cross A is reflexive, symmetric and transitive. What about the relation phi empty set, empty relation? Is it equivalence? No. Why? It is symmetric and transitive but not reflexive because it contains no element. Okay, since phi is not reflexive, it is not equivalence also. What about the relation identity relation? Yes, we mentioned it earlier that identity relation is equivalence. Okay, one more thing is that identity relation is the smallest equivalence relation on a set capital A. Okay, the smallest equivalence relation on a set A is the identity relation. If we delete any single element, any one element from the identity relation, that relation is not equivalence because it is not reflexive. Clear? From note number 4, we can say note number 5, that is the minimum number of elements in an equivalence relation on a set A is equal to the minimum number of elements in an equivalence relation, which is the minimal equivalence relation, which is the smallest equivalence relation, identity relation. How many elements are there in identity relation? It is equal to number of elements in A. Therefore, minimum number of elements in an equivalence relation on a set capital A is equal to, yes, number of A. Okay, number of A. If a set contains 50 elements, equivalence relation must contain 50 elements. Okay, if a set contains 10,000 elements, the equivalence relation must contain at least 10,000 elements. Clear? Yes. Now, we are going to learn next concept. Listen to the example carefully. Let S equals set 1, 2, 3, 4 and let R equals set 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, 2, 1. This is the example we discussed in the previous section. Okay. Now, is the relation is an equivalence relation? Is the relation equivalence? Yes, of course, because the relation is reflexive, symmetric and transitive. Now listen. How many elements are there in A? 1, 2, 3, 4. 4 elements are there. Okay. Which is the first one? That's 1. Now listen. Which are the elements in A related to 1? Which are the elements in A related to the first element 1? Which are the elements in A related to the first element 1? Okay. For that we look at the relation. 1 is related to 1. Therefore, one element is 1. Then another one. Here there is no 1. Okay. Here 1 is related to 2. Then 1 is related to 2 also. And 1 is related to 2. In short, the set of all elements related to 1 is set 1 and 2. 1 is not related to 3. 1 is not related to 4. 2 elements are related to 1. Let me write it. Set of all elements related to 1 is equal to set. It is a set of all elements in A related to 1. That's equal to set 1, 2. Clear? Now, what is the second element? 2. Then, which is the set of all elements related to 2? Set of all elements related to 2. Let us search. 2, 2. 2 is related to 2. Then 2, 1. 1 is related to 2. Then which are the elements in A related to 2? That is 1 and 2 again. 1 and 2 or set 2 1s. Set 2 1 is equal to set 1 2. In roster form, elements in which they are listed, the order in which the elements are listed has no importance. Okay. Then set of all elements related to 3. 3. Okay. Set of all elements related to 3. Only 3, 3. 3 is related to 3 itself. Therefore, set of elements related to 3 is set 3. And the last one, set of all elements related to 4. That is again 4, 4. There is another 4 here and there. Okay. Therefore, set of all elements related to 4 is what? Set 4. Okay. Listen. Set of all elements related to 1 is set 1, 2. Set of all elements related to 2 is set 2, 1. And so on. Here, set of all elements related to 1 is called equivalence class containing 1. What do we say? Equivalence class containing 1. Then set 1, 2 is the equivalence class containing 1. Okay. Set 1, 2 is the equivalence class containing 1. Why we say it as equivalence class? Because it is the product of a set and an equivalence relation. Okay. When a set and an equivalence relation is there, an equivalence class must be there. Therefore, we call it as equivalence class. Then what is equivalence class containing 1? Set of all elements related to 1. Okay. Then how can we write the second line? Set of all elements related to 2. Yes. Equivalence class containing 2. Equivalence class containing 2 is equal to set 1, 2 or set 2, 1. Okay. Then set of all elements related to 3. Equivalence class containing 3. That is equal to set 3. Set of all elements related to 4. Equivalence class containing 4. That is equal to set 4. Okay. It is often difficult to write equivalence class containing 1 always. In mathematics, we try to shorten every term. For example, the sum of 3 and 4 is equal to 7. We just say 3 plus 4 equals 7. In a similar manner, we write equivalence class containing 1 using this notation, that is class 1. Class 1 equals set 1, 2. Class 1 is equal to set 1, 2. These two are same. Class 1 is the equivalence class containing 1. Equivalence class containing 1 is set of all elements related to 1. In short, class 1 is the set of all elements related to 1 in A. That is 1 and 2. Therefore, class 1 equals set 1, 2. Therefore, equivalence class containing 2, class 2 equals set 1, 2. Equivalence class containing 3, class 3 equals set 3. Equivalence class containing 4, class 4 equal 4. Clear? I think all of you understood what I am saying, that equivalence class, different equivalence class is very simple. That is set of all elements related to an element in a set A under an equivalence relation. Clear? Now we are going to learn next. Just write the formal definition of equivalence class. An equivalence class, definition of equivalence class is this: R be an equivalence relation. For an equivalence class, there must be an equivalence relation and a set A, and small a be an arbitrary element in capital A. Small a be a member of A. Then the set of all elements related to A, set of all elements related to the element A in the set A under the relation R is called equivalence class containing A, and we denote it as class A. Okay, I think you clear this concept. Now write its mathematical version, that is equivalence class containing A equal to set of all x belongs to A such that equivalence class containing A is set of all x belongs to A, set of all elements in A. What is the peculiarity of this x? That x must be related to small a. This A, that x A belongs to R. Okay, therefore equivalence class containing A is a subset of capital A, is a subset of capital A. Elements in capital A which are related to small a in capital R. Clear? This is very important concept, equivalence class containing A. So tell with me, equivalence class containing A is equal to set of all x belongs to A such that ordered pair xa belongs to R. We can say this ordered pair xa as ordered pair ax also, because relation is equivalence, hence it is symmetric. Therefore whenever xa belongs to R, then ax also belongs to R. I think it is clear the concept equivalence class to you, that is equivalence class containing A is equal to set of all elements in A which are related to small a. Clear? Now we are going to the last concept of this section, relation. For that, take the previous example. S equals to 1, 2, 3, 4 and R is equal to 1, 1, 2, 2, 3, 3, 4 for 1, 2, 2, 1. Clearly it is an equivalence relation on A. Okay. Then what is class 1? Equivalence class containing 1? Yes. That is class 1 equals set 1, 2. What is class 2? That is again set 1, 2. Then class 3, set 3, and class 4 is equal to set 4. Okay. Listen, there are 4 classes, 2 of which are identical, class 1 and class 2. So we can say there are 3 classes. One is class 1, 2, next set 1, 2, next set 3 and set 4. Okay, it means that this set is divided into 3 pieces. First piece is set 1, 2, next one set 3 and set 4. I am going to draw the figure. Listen. Set A containing 4 elements 1, 2, 3, 4, and these 4 elements are divided into 3 pieces 1, 2, 3 and 4. 1, 2, 3 and 4. Okay, 1, 2 is a division or is a piece of the set A. Therefore we call this set as A1. Set 3, it is again a piece of the set A. Therefore we call that set as A2. And 4 is the third set, we call it as A3. This 3 set has some properties. A1, A2, A3 has some properties. Okay, these 3 are subsets of A and it possesses some properties. What is the first property? Listen, the first set, set 1, 2. Every element of this set A1 are related to each other. It means that 1, 1, 1, 2, 2, 1, 2, 2 belongs to R. See, 1, 1, 2, 2, 1, 2, 2, 1. Every element of this set A1 are related to each other. Now look at second set A2. Every element of this set. Here there is only one element. Therefore, 3, 3 belongs to R. Here 3, 3 belongs to R. What about the third set? 4. Set 4. 4, 4 belongs to R. In short, every element of A1 are related to each other, every element of A2 are related to each other, every element of A3 are related to each other. Okay, therefore the first property of these 3 subsets are every element of AI are related to each other. Every element of AI, A1, A2, A3 are related to each other. Okay, now second property is any element of A1 related to any element of A2? Any element of A1 related to any element of A2? No. Why? There is no 1, 3 here, 2, 3, 3, 2, 3, 1. It is not an element of this relation. in a similar way, 3 4 does not belongs to R, 4 3 does not belongs to R, 2 4 does not belongs to R, 1 4 does not belongs to R, 4 1 does not belongs to R. It means that no element of A1 is related to any element of A2, no element of A2 is related to any element of A3, no element of A1 is related to any element of A3. In short, no element of AI is related to any element of AJ if I and J are different. Okay, that is a second property. No element of AI is related to any element of AJ if I is not equal to J. And the third property, listen, what is the intersection of these two sets, A1 and A2? Is there any common element? 1, 2, 3, is there any common element? No. Therefore, A1 intersection A2 equal to 5. What about A2 and A3? A2 intersection A3, it is again 5. What about A1 and A3? A1 intersection A3, there is no common element and hence its intersection is 5. It means that AI intersection AJ equal to 5 if I and J are different. One more thing is that what is the union? A1 union A2 union A3, that is set 1 2 union set 3 union set 4, set 1 2 union set 3 union set 4. It is equal to set 1 2 3 4, that is nothing but A, that is union equal to A, total union equal to A, and pairwise intersection equal to 5. That is the third property. AI intersection AJ equal to 5 if I not equal J, and A1 union A2 union A3 equal A, that is the union equal A. It means that these three subsets of A satisfies these three conditions. Every element of AI are related to each other. No element of AI is related to any element of AJ. Pairwise intersection is 5 and total union is A. If any three sets satisfying these three conditions are called partitions or subdivisions of capital A. Hence, A1, A2 and A3 form a partition of A. A1, A2 and A3 form a partition of A. Then what is a partition? Partition means three or more subsets, number of subsets of a set satisfying three conditions. First condition is every elements in AI are related to each other. No element of AI is related to any element of AJ, and pairwise intersection equal to 5 and union equal to A. Clear? Now let us write its formal definition. Let R be an equivalence relation of on a set A. Okay. To define a partition, there must be a set. There must be a relation R, it should be equivalence, and it must be defined on A. Then R be an equivalence relation on A, and let R divides A, capital A, the entire set into mutually disjoint subsets AI are equivalence classes. In the previous example, A1, A2 and A3. Three conditions are there. First condition is all elements of AI are related to each other for every I. All elements of AI are related to each other. Second one, no element of AI is related to any element of AJ if I not equal J. And third one, AI intersection AJ equal 5 if I not equal J. Pairwise intersection equal 5 and total union equal to A. If these three conditions are satisfied by these subsets AI, then AI are called partitions or subdivisions of the set A. I think all of you clear this concept. A little bit difficult, so learn it well, very important one also. Okay, now let us draw its graph here. This is the set A, and I am going to partition this A into different pieces, and its name is A1, A2, A3, A4, A5, A6, etc. AN. What is the properties of this AI? Union equal to A, intersection equal to 5, AI are related to each other, no AI is related to any element of AJ. Therefore, this is the representation of a partition of a set capital A. Okay, today's chapter is over. The notes you want to write in your notebook is attached in the description box. You can write it well, and if you think my classes are useful to you, you please like, share and subscribe as the classes to get more videos and classes. Okay, thank you for watching. Goodbye.